Okay, hi. So now this is our fourth video, and the goal is to prove some corollaries of the main result that they proved in the last video. So last video we proved theorem 51 of the textbook, and today we're gonna see some consequences of that. So let's recall the result that we proved. Suppose sigma is an isomorphism from f to f prime, and f is a polynomial with coefficients in f, E is a splitting field of f, and E prime is a splitting field of sigma star f. And then the first assertion was that then there's going to be an isomorphism from E to E prime, which extends the isomorphism sigma from f to f prime. And then after that, the second, and then after that, there was also an assertion about the number of such sigma hats, and we showed that if every irreducible factor of f is separable, then the number of sigma hats, so the number of extensions of a sigma to an isomorphism from E to E prime is exactly the degree of the extension E over F. Well, I mean, we also actually proved that in general, so if you don't assume that the irreducible factors of F are separable, then the number of sigma hats will be at most this many. But if the irreducible factors of F are separable, then the number of sigma hats will be exactly equal to that. So the goal of this video is to prove some corollaries of this. So let's start with the first result. So let's call this corollary 1. Any two, so let f be a polynomial with coefficients in f, any two splitting fields of f over f are isomorphic via an isomorphism that fixes f. So this fixing f, it means that, so this portion here fixes f, i.e. acting like identity on f. So what's the proof? The proof is right away from the previous result. You're going to look at f, here the identity map. It's clearly an isomorphism. Make sure that we don't lose the camera. Okay, so we take the identity map on f, and now take E and E prime, two splitting fields of, so here E and E prime are two splitting fields of f over f. And the previous theorem tells us that there's an isomorphism from E to E prime which extends this isomorphism on f. Right? So then the previous theorem, there exists an isomorphism. Let's call that maybe tau, if you wish, from E to E prime, which extends such that tau is equal to identity on f. The previous notation that we had, this tau will be what we called identity hats. Okay, so that's the first corollary. That given any polynomial f with coefficients in the field f, any two splitting fields of the polynomial over f are isomorphic to each other with an isomorphism that fixes f. So, in a lot of results that we have, a lot of things that you read, you see that they are talking about the splitting field of a given polynomial over a field. Now, the splitting field is not actually unique, but as you can see, it is unique up to an isomorphism that fixes the field f. Okay, good. So that was the first corollary. Second corollary is the corollary of this one, actually, of the first corollary. The following very interesting result, number 2. Any two finite fields of the same cardinality are isomorphic. Proof. Okay, so we already know that the cardinality of any finite field is a power of a prime number, that prime number being the characteristic of the field. So we'll now suppose E and E prime have cardinality Q, which is P to some power n. P a prime number. Then so let let f, respectively f prime, be the prime field of E and respectively E prime. So now here's our picture. Remember, the prime field, so these fields have characteristic P. The prime field is a copy of Fp. So F and F prime, well, there's a unique isomorphism between them. Right? Just send 1 to 1. And then, so E, well, contains F, E prime contains F prime. Another, look, I mean, as we've seen this result before, if E has P to the power of n elements, it'll be the splitting field. This is a splitting field of x to the power of q minus x. Remember, I mean, this was something that you showed a long time ago in your homework. So any element of, so if E is a field with q elements, using Lagrange's theorem from group theory, you can see that every element of E is a root of this polynomial. Every element of E is a root of this polynomial, and then, well, E has q elements. That's already q roots for this polynomial, and the polynomial has degree q, so, well, those are all the roots of this polynomial. This polynomial, it has q roots in here, it splits there. And then, well, every element of this guy's of E is actually a root, so E will be the splitting field of this polynomial. So splitting field of this over the prime field F, and then similarly E prime is a splitting field of the same polynomial over F prime. And now, so actually the way I gave this proof, this will be corollary of our original statement, not the previous corollary. But now we just apply the result that we had, the first result, the result from last video. So you've got these two fields isomorphic to each other via this isomorphism, this canonical isomorphism. This is a splitting field of this polynomial, is a splitting field of that, A prime is a splitting of that same polynomial. And by the way, this polynomial is, well, if you apply this isomorphism to the coefficients of this polynomial, you would get the same polynomial, but now as a polynomial with coefficients in f prime. So the first result, the result from last video says that there's going to be an isomorphism from E to E prime extending this isomorphism. So there's an isomorphism, and we call this maybe, if you like, let's call this sigma, and then there's an isomorphism, sigma hat, from E to E prime, extending sigma. So that shows that E and E prime are isomorphic to each other. So any two fields with Q elements are isomorphic to each other. Now, because of this, often, people talk about the field with Q elements. There isn't being that, well, they are all isomorphic to each other. So, there's this standard notation that sometimes people use, boldface F with a Q here. This is for field with Q elements. They're all isomorphic to each other. Okay, good. So that was the second corollary. And then one last corollary. Okay, now let me remind you of a definition from a couple of lectures before, a couple of lectures ago. So this definition is crucial for all the rest of the course. So definition, let K over F be a field extension define Galois group of K over F. So this you're going to read it as the Galois group of K over F to be the following group. To be the following. So let me define it as a set, and then we'll discuss that it's actually a group. So this consists of isomorphisms, so sigma from K to K, such that sigma is an isomorphism. And moreover, sigma fixes F. Sigma of A is equal to A for every A in F. So in other words, sigma is equal to identity on F.